So in the past talk, we talked about complexity in biology. Now we are talking about the complex interactions of elementary particles and therefore switch to high energy physics. And you probably all know about the LHC, the Large Hadron Collider. But there's also other interesting experiments, and Christian will tell us about. So please give a warm welcome to Christian and enjoy the talk.
Yeah, hi, thanks a lot. Thanks for having me. It's awesome to see so many people. So first of all, now that I start, a short disclaimer, I am part of the Belle II experiment, and I will use this as an example, but this is not an official Belle II talk, political reasons. And on the other side, it's high energy physics. It's very complicated, so I will have to simplify and slightly oversimplify a few things. You will see, but I hope it's still okay and you will learn something from the talk. So actually, where do we come from? So the universe started roughly 13.8 billion years ago with a Big Bang. And this is the picture on the top right. Then it evolved. There was already talks about Euclid, searching for dark energy, for example, today. And from our standpoint, everything looks the same. This is the picture on the bottom right. So we have a cosmic microwave background radiation with a temperature of 2.7 Kelvin, and what you can see there is the fluctuations on the order of 10 to the minus 4 Kelvin. So it's very small fluctuations, so it literally just looks the same from everywhere. But also, from first principles, there should have been equal amounts of matter and antimatter at the Big Bang. But we also know by now that there's some imbalance because we are here, and this imbalance is actually 1 to roughly 5 billion from the order of magnitude, so it's quite small. But the question then is, where do we actually come from and how did this evolve? So what is high energy physics about? Let's go from huge to tiny. So we go from the very large scales, galaxy clusters. If you want to hear more about this, for example, listen to the Euclid talk again. Then we go to large scales, which is on the order of several thousand or maybe millions of kilometers or billions of kilometers, like solar systems and stars and so on. Our daily life, we know, of course, best. We can grasp orders of millimeters, maybe slightly smaller, and up to thousands of kilometers. I mean, many of us have flown to distant places, thousands of kilometers away. Then we all go further down to the micro and nano scale, which is on the order of micrometer to maybe nanometer. This is where bacteria and viruses live, for example. And then we go to the atomic scale, which is smaller than a nanometer, much smaller actually, but high energy physics is even much smaller than that. So here we are talking about length scales that are less than a femtometer, and a femtometer is 10 to the negative 15 meters. So it's really, really tiny. 10 to the minus 15 meters actually is the size of a proton. And this is one of the base particles that we exist of, and it's the part of the hydrogen atom. So it's really tiny scales, and that's also why I don't really have a picture. I mean, this is, for the atoms, it's some artificial picture of trying to show what's going on, but for high energy physics, it's really difficult to have a clear picture of what's going on because it's just too small. Here we have then the standard model of high energy physics. High energy physics is abbreviated with HEP. The standard model is what describes our world. It's a very successful model and a theory of the nanoscopic world. It involves particles and antiparticles and bound states, and you can see the particles that we know of, the fundamental particles on the top right. We have 6 so-called quarks and 2 generations, or two charges. A couple of them, 3 of them are charged with 3/3 of an elementary charge, and the others have a negative 1/3 charge. Then we have the so-called leptons. These are electron and its heavier brothers, the muon and the tau lepton. And then we have something that is called neutrinos, and in the standard model they are massless. Then we have the force carriers, which are the photon here. These are the carriers of the electroweak force, and then the Higgs boson that essentially gives mass to these particles, and was found 12 years ago. But we by now know that the standard model has some shortcomings. First of all, we know that neutrinos are not massless, although in the standard model they really should be. So where do these masses come from? So this already indicates that the standard model cannot be all that there is. Also, the standard model only describes 5% of the universe entirely. It does not contain dark matter and dark energy, and we know that both of these exist. For example, from these rotational curves of galaxies, this is what the rotational curves of the velocities of the stars in the galaxy should look like as a function of the distance of the center, with just the visible energy, and this is what we observe. So there must be more mass driving these rotational curves. And also, pointing back to the Euclid talk, we have no idea what these 70% are, this dark energy. We know that there's something that blows the universe out and it grows faster and faster, but we have no idea what it is. And still, the standard model that we have so far cannot explain at all what antimatter is. And then the question is, where did all the antimatter go? I mean, it can explain some parts, but not everything. And essentially, we could call this an illegal instruction, borrowing from the topic of this year's C3. Of course, it's not an illegal instruction in the sense of the nature, but just that our model isn't enough yet. There are currently 3 frontiers of flavors in high-energy physics. The first is the energy frontier, so you push to even higher and higher energies. This is, for example, what the LHC does and what most people know. I think if they know something about high-energy physics, they likely think about the Large Hadron Collider and at CERN. And often this involves high direct discoveries of new particles by some means or another. But one does not have simply have one ring to rule them all. So then the second flavor of high-energy physics is the so-called astrophysics frontier. There, physicists and scientists check what the particles from astrophysical sources do, like neutrinos, photons, and charged particles that come from maybe even far galaxies and so on to us. Some experiments like these are IceCube at the South Pole, Super Kamiokande in Japan, and a few others that really check these high energetic particles that travel billions of light years to us sometimes. And lastly, we have the so-called precision or intensity frontier. These usually are dedicated experiments at way lower energies. So at the high energy, at the LHC, we talk about energies of TeV, so 10 to the 12 electron volt. At these precision machines, we usually are 3 orders of magnitude less. Often we are trying to do indirect discoveries of new particles, and what this is I will come to in a minute. And examples for these are the past experiments Babar and Belle. I'm currently running our BES III and Belle II, but of course also the LHC experiments can do part of precision physics by really measuring process precisely, and then there's another big important experiment currently ongoing, which is the G-2 experiment. So what is the difference between direct and indirect measurements? Direct measurements, for example, or discoveries, is what we see on the left. This is a plot from the Higgs discovery, and you can see here a background distribution, and then you can see some tiny excess. Here, it's not really huge, and then we found that this has a lot of the properties that we expect from the Higgs boson. The indirect approach is then finding tiny deviations from the standard model predictions, often in very rare processes. Both can give hints to new physics. I mean, if we found a new bump like this somewhere at high energies, we could be pretty sure that there's a new particle that maybe we do not yet understand. But for example, if this tiny bump was 10% larger or smaller, we would be, this doesn't really fit what we expect from the Higgs. So is there something more to the Higgs model itself? Where do these deviations come from? And the experiment that I'm working on focuses mostly on these indirect measurements, but really measuring processes very precisely. So yeah, what is then precision physics? I already said these new physics effects must be really, really tiny, like 10 to the negative, like 5, 10 orders of magnitude smaller than we currently see sometimes. or they start playing a role at higher energies. For example, at the LHC, it might be that we could find new particles at the LHC still, but only if we go like a factor 10 higher in energies again. What is common to all experiments is that we collect large data sets to measure all the deviations, the small deviations from the standard model, and these vary via the indirect effects, like something contributing where it shouldn't, and then that we see that there's something a bit more and something a bit less than we expect. And then the more data we have, we can be really strict on which data we keep in our analysis and which data we throw away to have a very pure sample. And usually we do this precision physics often by colliding electrons. So as an example here, you can imagine that colliding protons as the LHC is like colliding two cars. You see a lot of debris going in all directions, and there's a lot of stuff going on. And colliding electrons is really like a simple mathematical model, for example, just colliding two steel balls. They bounce off each other and then go in directions that you can calculate from the velocities and the angle relative to each other. And the formula down here, I promise it's the only formula in the talk, calculates these angles in 3 dimensions. And of course, if you would find that these formula do not really match what we see, you could also see something, but it's very clear at the beginning. Then how do we do this? I already said we start from a very well-known initial state. Electrons and positrons, if they collide, they just form a photon, essentially, or some other particles that then create new particles. These new particles we get from Einstein, essentially, E equals mass times speed of light squared. And then we can use this energy to roughly steer where we want to work with. And this plot on the bottom right is, for example, from a pretty early experiment. You can see here a lot of bumps. And on the x-axis, you see the mass of the particle, or this energy here. And what we are then interested in our experiment is this threshold where we can create 2 B mesons. A B meson is based on a beauty quark. We also call it a B factory or beauty factory, and we operate at this bump because then we quite often create these particles. But there's also another experiment doing something similar, but at lower energies. It's the BES III experiment in China, and it's a so-called charm and tau factory, because at roughly 3.5 GeV, you can, for example, produce 2 of these tau leptons. And because we have the flavors are called, the charm and beauty are the flavors of the quarks, we call these then also precision physics or flavor physics. What are these other particles? Now we get to the really oversimplified part. So first of all, we distinguish 2 types of composite particles. First of all, mesons. They combine a particle with an antiparticle, and then hadrons, which usually combine 3 quarks. And if you click on the link, this is a link to the list of all particles that we know of on Wikipedia, and there are a lot of them. Usually heavier particles decay to lighter particles. And then there are other particles radiated off in this process, and then we can measure these. And in the end, there are only few particles that we consider stable because they live on the order of a few microseconds. Some of them live longer, but a couple of microseconds usually is the best we can get from these stable particles. For example, then we can start with what we call quarkonium. This is a bound state of a B quark and an anti-B quark, or C quark and an anti-C quark. And these are pictures of the particle zoo, how we call it, for the B's and C's. Then the B meson that I already mentioned consists of a B quark and a lighter anti-quark. Then here we have a B quark, and then the 3 U, D, and S quarks as an anti-quark. Then we have the D mesons that are a C quark and a lighter anti-quark again, UDSC. The so-called K mesons, which are even lighter than the D mesons. And then in the end, we have the lightest mesons. They usually are what we call stable, in the order of or many of them are stable in the order of couple microseconds. And if they decay, this is what we can see in the detector. And then on the other hand, there are hadrons. First of all, the proton and the neutron. These are the particles that we consist of. So all of us are made from protons, neutrons, and electrons. There are many other, but I didn't even attempt to list them here. But hadrons, as I said, contain 3 quarks. Now coming to the Belle II experiment that I'm working with. It's contrary to the LHC, it's not located in Geneva in Switzerland, but it's actually located at the so-called SuperKEK-B accelerator at the KEK laboratory in Tsukuba in Japan. And I now see that there was supposed to be an emoji, it went missing. So we are over 1,000 people by now working on this experiment, but of course there have been even more working on the experiment in the past. Already said, B factories usually are called B factories because they are meant to produce these B mesons, but we cannot avoid also creating charm mesons and tau leptons, so we can do our flavor physics with all of these particles. So you can see here, this is the larger Tokyo area, and the Belle II experiment is located here. And this is a brief overview of how the detector looks like. So it's 7.4 meters long and 7 meters high and in diameter, essentially. So what does a particle detector usually consist of? So we start at the interaction point, which is just this black dot here. Then this is true for Belle II, but also for other experiments. We have the so-called vertexing detector. Usually by now this is a silicon pixel detector with pixel sizes in the order of few 10 micrometer, maybe 100 micrometer. This is nothing compared to your cell phone camera that usually has pixels that are way smaller than a micrometer by now, but it's enough for us. And by now we usually have millions up to billions of pixels in a modern detector. This is then surrounded by a tracking and maybe vertexing detector in case of Belle II. Often we use silicon strips. They are tiny strips that in one direction just have like 100 micrometer in size or 200 or so, and the other direction they really span over centimeters. Depending on the detector, these can also be several millions. Then we have the so-called tracking detector. In Belle II, it's a gaseous detector where the particles pass through, ionize the gas, and then we can measure where the particles went from the ionized gas. Other experiments use other technologies as well. But yeah, I'm sticking with Belle II for now. Then we also have to measure the energy of the particles, which is called a colorimeter. Usually, or very often, it's high purity crystals or scintillators. So the particle goes in these crystals, and because they are so dense, the particles are essentially stopped, at least most of them. Some make it through, but it's only certain types that just make it through. And because they are a bit more tricky, we also have so-called K-long and muon system, which is the outermost part. K-longs are special in that sense. They are hadrons, or they are mesons, but they have a very long lifetime, and essentially, because they're neutral, they don't interact with with material much. So they essentially fly out and can be stopped in this K-long system. And muons are just like, I don't care what material you put there, I give you a little signal and then I just fly out. And because we can be pretty sure that if we can see a track in this part and something in here, that this likely has been a muon. So we need these additional outer detectors. And this is essentially how all detectors are built, either in a concentric way like here, but there are also other experiments where these different types of detector are stacked behind each other over several meters, for example, in LHCb. But we need these types of detectors to see where our particles are actually going. This is a bit better view, so you can roughly see that the actual picture is better reassembled here. Here the vertexing and tracking and vertexing detector are in the innermost ring. Then we have the actual tracking detector, the gas detector here, followed by the colorimeter. All of this is enclosed in a magnetic field, which is really important. And then we have the K-long and muon system in the really outer part. And if we add then a few particles, it looks like this. So you can see there are tracks that are curled due to the magnetic field. Some particles just go out. These, for example, would be photons because they just don't interact, but these crystals just stop them. And for example, this is a muon. It just goes here. And goes also to the outside world. So if we see this in a detector, we can be pretty sure we found a muon. Now, what are the actual flavor physics in Belle II? B mesons, as the other mesons, usually decay to lighter particles. And the most forward process that we have is so-called tree decay. Why a tree decay? Well, because this part, looks like a tree. So we have some particle that decays, produces a few other particles, and what we then would measure in this process, for example, is how often does it happen, which is defined by this part. This is the constant that says how often does this B quark here go to a charm quark. And if we measure this precisely, we can roughly say how good this is. And of course, if we see that this happens more often or less often than we expect, we might find new physics. In addition to that, we have the loop decays. These are a bit more complicated. So they're called loop decays because, well, here you have some sort of loop. There are additional particles going here, then there's a photon radiated off, and the B quark then can go to a D quark or an S quark. And the interesting thing here is these new physics effects that we are searching for in high energy physics and in flavor physics can hide in these loops. It's easier to hide in here than here, and then we can see small effects. So far, we have found the Higgs boson 12 years ago, but we know that it's uncharged. Its charge is 0, but you can see here there's a charged particle, and it might just be that in one of these processes, there could be a charged Higgs boson hidden there and then slightly enhance the rate of what we see or decrease it even, depending on how these couplings work. And this is the very interesting part. We really have to do this, study this process in very much detail to understand what happens in there and do we maybe have contributions from new particles. There's no need for just a Higgs boson, for the charged Higgs boson. It could also be dark matter that we are searching for since quite some time and while we know that they exist. So how do we take the data then? We have really high frequencies. So our electron and positron branches cross each other every 4 nanosecond. This is 250 megahertz of frequency. Something interesting then happens every 30 kilohertz, with 30 kilohertz roughly. For this we have the first level trigger, what we call it, which is based on FPGAs. Not going into details here, there was a talk on FPGAs 2 hours ago or so, also here in this room. So we take all the data from the detector. This is several hundreds of gigabytes maybe per second maybe, analyze them briefly, and then decide for some of these events, they are interesting enough for us to investigate further. So the latency in this system here is 5 microseconds. So you have 5 microseconds to get all the data, analyze them briefly, and then decide interesting or not interesting. So these events that then go out with 30 kilohertz go to what we call the high-level trigger. It's a CPU farm. Currently, I think 9,000 CPU cores, and it might get a few more in the future. And this does the final event selection. The output is still a few kilohertz, maybe, and we still write orders of gigabyte per second to disk once we are on the final stage. So, and the disk, or the storage is not just hard drives that you all know. May I just ask, who has heard of tape storage? Quite some people, but I know where I am, so not, not surprising. Yeah, so first of all, we store data to disk, analyze them further, and then in the end, we store them to tape, and we need terabytes and petabytes of tape storage to store all of our data. Of course, we cannot just go to some big company and say, please build us a detector and write the software and do all the readout. It's all custom-made hardware and software. For the detector and the readout, already said the detector readout is mostly done on FPGAs. Other detectors by now use, for example, also GPUs. The software usually is written in C, C++, and Python, at least in our case. And yeah, and to compare this with the LHC, there the collisions are taking place every 25 nanoseconds, so with 40 megahertz. Then there's the first pre-selection on the detector level. But the output of the level 1 trigger is still in the order of 100 kilohertz. So we reduce the data from here to here by a factor of 400 in terms of the in the LHC. Then we have an additional stage which is called the L2, which is a CPU farm as here. And there the output is on the order of 1 kilohertz. And then we have the final event selection with the high-level trigger. And there the output actually is couple hundred hertz, but it's still 10 gigabytes per second. The reconstruction software, it's all self-developed. I already said we cannot just go to Big Blue, the FANG companies, or SAP, or whoever, and ask them to build software for us, because we are the ones that built the detector. We know best what the detector can do and can't. So there are a lot of, for example, also PhD theses and so on that go into developing this software. In the case of Belle II, this software has been developed over more than 10 years. It's done in C++ and Python mostly, also some Fortran. So far, it only works with x86 processors. And at all stages, we are increasing the use of machine learning in the reconstruction, but also later on in the analysis. But we also rely heavily on external software, and usually this is open source software, but under very different licenses, which are often like a bit contradicting. So yeah, you can use our code, but you cannot modify it, or you can, but whatever. Everything is based on the root software that was developed by CERN. It's the go-to standard, essentially, in high-energy physics. I think every experiment uses root as the core, because it's like a Swiss knife for us. It has a lot of functionality that we really need for all experiments. Then we use something that is called generators. Their theorists usually implement their theories, their theoretical models in code, and then give it to people like us, experimentalists, to use it. And this is actually where most of the Fortran code is coming from, because it's fast, reliable, and many of these software packages are like 30 years old. They are not touched, because the re-evaluating all the software after rewriting it in C++, Rust, whatever, will take so much more time that people are just, okay, maybe better learn Fortran. It's debatable whether this is a good idea or not, but yeah. And then, of course, many Python packages for various purposes, machine learning, NumPy, and a lot of others, of course, for plotting. And then coming to other software, for other experiments, there the software development might even have been going on for 20 or 30 years. Atlas, CMS, these detectors have been planned in the 90s, and they are now in operation. So sometimes the software really has developed over decades. Coding standards have changed. C++, for example, has changed quite a lot in this time. Sometimes it's rewritten, but never changed the running system. And in addition, other experiments then also use Java. Julia is starting to come up. CUDA for the GPU acceleration. Often it's still only x86, so AMD or Intel CPUs that are used, but these parts here below here are the same. The generators in the physics models that are implemented in code are usually the same everywhere, or very similar at least. Now coming to the bigger picture. All experiments really want to get more precise, and this is in all aspects. Also we want to take 10 times more data per second than we currently do. So then in addition, we want to get more granular. More granular detector means we're going from hundreds of micrometers for pixels to 20 micrometer in pixel size, which means that you will have hits and signal in way more pixels, so you will have way more data coming from your detector, and then it could be that you have terabyte of data per second coming from a detector that you have to digest in your readout system, further analyze, and then store. And so this has a real big impact on the trigger systems that tell you this event looks interesting or not, and also all the software that comes behind that trigger system, and also the offline software. And this is from a plot from the Atlas collaboration, because they now really want to ramp up the amount of collisions they have per bunch crossing of the protons. And you can see here that they start here, and now that they go to what they call the high Lumi phase, this is what they expect. So it might be that they need 16 times more computational power than what they currently have. Just having your computer farm increase by factor 16 isn't really reliable. In the end, you would also need 16 times more storage and so on. So it's really difficult to just ramp up and say, oh yeah, let's go to higher event rates and better detectors. And in addition, this is only the data part. We usually do what we call a blinded analysis. We use these we use detector simulation, throw our events in, simulate all the detectors, and then all the event selections there. And only once we know on simulated data that we want to use this analysis as it is, we just go and really look at the data. It's like a blinded analysis for doctors where they don't know whether you get the medication or a placebo. It's similar for us, but we have to do this with simulated data. But usually you want to have at least as many simulated data as you have actual data, sometimes even more, like factor 10 sometimes. And of course, if you increase your data rate by factor 10, you also have to increase your simulated data by factor 10, and then it really gets complicated. So we need huge computation infrastructure and very performant and efficient software for both CPU and memory. And there, over the last 20 years, the large worldwide grid was brought to life. It's a distributed computing system all over the world. Currently, it consists of more than 1.4 million cores, 1.5 exabyte of storage on both disk and tape, on 170 sites all over the world, used by all big experiments, and by now also astrophysics and others come in, because if there's an infrastructure, why not use it instead of building it from scratch? And of course, this is only possible due to the World Wide Web, which all of you, I guess, know also was envisioned and started at CERN. And in many parts, we are using machine learning more and more. I don't know any analysis, modern analysis, in any field of high-energy physics that does not use machine learning in some part. It's really an important tool. Some people might still debate whether the Nobel Prize this year for physics was given to people who developed machine learning and neural networks in the first place. I'm not going to start participating in this. But in the end, there's also growing interest in detector simulation using neural networks. For example, simulating all these calorimeters is very cost intensive. It can take up to several seconds to just simulate one particle being stopped in there. And machine learning algorithms have shown to improve this by up to orders of magnitude, like 10 times, 100 times, maybe 1,000 times faster even, while providing the same accuracy. And this, of course, can really impact on what we can do in our simulation if we can just simulate everything 10 times faster, for example, or 100 times faster. So to summarize, high-energy physics is really way more than CERN and the LHC experiments. Flavor physics is exciting and can really lead to interesting insights that can benefit all of us. And a lot of research on where we actually come from is not only done at the LHC, but also on the smaller experiments around the world. But of course, this is only possible with large collaborations in the order of tens, hundreds or thousands of people. And we are trying to investigate these illegal instructions of the universe and the standard model, improve our standard model, try to find missing antimatter, dark matter, and dark energy. And of course, this also requires cutting-edge technology, and high-energy physics without machine learning would be nearly impossible. And thanks you.
Thank you very much for this nice introduction. Are there questions? If you leave the room, please do so quietly. And we start with microphone 3.
Okay, hey, thank you for your good talk. Very interesting. You mentioned that your detector was in Japan. And if I think of Japan, I think of earthquakes sometimes.
Naturally, yeah.
Does that influence each other?
Partially. So usually if there's an earthquake, for example, the colliding beams are thrown away as quickly as possible so that they don't go bonkers on our detector, and we just stop operation if there's an earthquake. This happens automatically. So if there's an earthquake detected, which, as you said, happens quite regularly, it might be that we would need a new, what we call alignment afterwards, because then due to the earthquake, the parts shift a bit, but we just restart data taking, and usually these shifts are only in the orders of micrometers maybe. So we just automatically calibrate this away in the end, or semi-automatically by now. But yes, of course, it has an impact.
And we go to microphone 1.
Yeah, hello. So thank you for your talk and oversimplifying for us mortals so we can understand what you are doing. My question would be on the software stack where you explain the detection and then the rest of the things. So for the FPGA part, my question would be that now when you say you want to go more, like 10 times or 100 times more, then the first stage would be the detection by the FPGA, some RF and all that you need, and then convert it to digital, because everything is analog, right, at the first stage.
Yes.
Right? And then you would need to convert this analog to digital. So do we have, as of now, I know only these RF socks from Xilinx that give this kind of a range, but do you have that kind of FPGAs, or what you are currently using, or what you plan to use in future? Maybe you can help us.
As far as I know, the conversion to digital already happens on the detector side, so the FPGAs only get digital information. And if the FPGAs in the trigger system, for example, say, oh yeah, this event is okay, they send back a signal to the detectors, and then the detectors send this digital signal to the readout system. But there are ideas of passing everything just through the FPGA and not having the FPGA analyze data and then telling the detector, but really everything that goes into the FPGA that is accepted goes out that way, and that's the only way out. But there are also other concepts. For example, LHCb plans or is already doing this. They don't have these trigger stages anymore. They just collect everything they get and throw it onto GPU farm with a lot of compute power in GPUs. Of course, the FPGAs are also employed on the detector level. So you get these information in digitized form, but then you have to add a few more information, store them somewhere, maybe do some additional analysis before you send them out. So FPGAs are also involved there.
And these are all Xilinx FPGA generally? Or?
I don't know. For us, I think mostly yes, but I cannot make a statement about other experiments, really.
The next question goes to the internet.
Hi, thank you for the great talk. The internet has a more general question. Do any of the existing colliders have technology to capture particles for further study?
I'm not sure what capture means in this case. Like, sorry.
Storage, I guess.
Yeah, so in general, it's not advisable to store all the data, because just it is just not interesting in the first place, although the trigger might say yes, but also some of the experiments, we usually store all of the particles and all the detector events that we then have, but other experiments might already say, but we only want to store a certain subset of the particles that are seen in the event, because the rest anyway is not interesting. But it really depends on the experiments, and I don't know the details about all the other experiments.
Microphone 2, please.
Thank you so much for the detailed and intensive talk. My question would be that whenever I read articles about finding these small particles, actually there is an underlying narrative to it that we just need more time, we just need more energy and money to spend on it to find the smallest existing ones and to find a lot of answers to our world and the way how we are living. And I would be really interested in your opinion if there is a reality to it to find the smallest one, or is it an infinite thing? What do you think?
I currently don't know really an answer, but maybe we can discuss outside after the talk. Sorry. I also think time is up. Not sure.
Well, I think we still can go back to the internet. Maybe it has...
There's another question from the internet, which is, what are the material limits to what kind of particles we can currently detect? What would be needed in terms of materials to detect new particles that we cannot currently detect?
It's not really about the material. So, for example, at the LHC, the goal is just to have high energies, maybe build a new accelerator, then not 27 kilometers long, but the idea currently is 100 kilometers, because then you can really go up in energy by an order of magnitude or so. Yeah, it's not the material that is limiting us, but it's how well we can analyze the data. That's also why the plan is to go to more granular detectors, because if you can better measure where the particles are going, you might be able to find hints to new physics better, but there are no material limits except for maybe detector limits. If your detector gets too warm because you want to read out too fast, then either you have to cool it better or reduce the amount of heat it produces. So maybe we would need to go to something beyond semiconductors or whatever, but this is just pure speculation. Don't quote me on that.
So unfortunately, we have reached the end of our time, but I'm sure you can still talk to our speaker afterwards. So let's thank him again.